At first glance, this expression looks like mathematical nonsense. Cosine of I factorial. We are forcing together three contradictory worlds. We have cosine, which is usually for angles and waves, the imaginary unit I, which doesn't exist on the real number line, and the factorial, which is strictly for counting whole numbers. How do you calculate the factorial of an imaginary angle? It feels illegal, but surprisingly, this has a real solution. Let's solve it. In our previous video, we showed the transformation for cosine of I. Now, let's actually visualize it. Watch the complex plane warp. The vertical lines stretch into hyperbolas, while horizontal lines curl into ellipses. Standard angles stay trapped between -1 and 1, but the imaginary unit I breaks out. It lands strictly on the real number line, right at 154. Okay, let's evaluate cosine of I. First question, what angle is I? It isn't an angle, so we use the exponential definition from Euler's identity, e to the ix equals cosine x plus I sine x. Now write the conjugate, e to the negative ix equals cosine x minus I sine x. Add them and the sine a terms cancel. That gives e to the ix plus e to the negative ix equals 2 cosine x. So, cosine x equals 1/2 times e to the ix plus e to the negative ix. Now plug in x equals I. We get cosine of I equals 1/2 times e to the I times I plus e to the negative I times I. And I times I is -1. So this becomes 1/2 times e to the -1 plus e to the 1. That's e plus e to the -1 over 2, which is hyperbolic cosine of 1, or cosh 1. Numerically, it's about 1.543, so the expression is really 1.543 factorial, and now we need a factorial for non-integers. Now we hit the weird part, 1.543 factorial. Because factorial is normally an integer machine. For an integer n, we define n factorial equals n times n minus 1 times n minus 2, all the way to 1. So 4 factorial is 4 times 3 times 2 times 1, which is 24. But the key idea is the pattern. N factorial equals n times n minus 1 factorial. That recursion feels like it should extend smoothly, but the usual definition only works on integers. So mathematicians use a continuous extension called the gamma function. It's built so that gamma of n plus 1 equals n factorial, and it keeps the same recursion for non-integers. Gamma of z plus 1 equals z times gamma of z. So factorial becomes a smooth curve instead of just isolated dots. That means we can finally interpret this. 1.543 factorial equals gamma of 2.543. So now let's calculate 1.543 factorial using the gamma function. Now we're going to compute that factorial using the gamma function. We already found cosine of I is about 1.543, so the expression becomes 1.543 factorial, which we define as gamma of 2.543. And gamma is literally an area. Gamma of z equals the integral from 0 to infinity of t to the z minus 1 times e to the negative t dt. Now plug in z equals 2.543. Gamma of 2.543 equals the integral from 0 to infinity of t to the 1.543 times e to the negative t dt. So picture the curve, f of t equals t to the 1.543 times e to the negative t. It rises, peaks near t equals 1.543, then drops fast. And numerically, that area is about 1.371. So the final chain is cosine of I is about 1.543, and cosine of I factorial is about 1.371. So we actually arrived. Cosine of I factorial isn't nonsense, it's just hidden behind definitions. First, we rewrote cosine of I using exponentials, and it turned into cosh of 1, about 1.543. Then we extended factorial with the gamma function, so non-integers finally make sense. And when we compute that gamma integral, the imaginary number collapses to a clean real value. Cosine of I factorial is approximately 1.38. Imaginary input, real answer. Thanks for watching.